Hi everyone, my name is Ushnish Sengupta. I'm early stage researcher number 1 within the Magister consortium. I'm doing my PhD in the University of Cambridge under the supervision of Professors Carl Rasmussen and Matthew Juniper. My research looks at Bayesian machine learning tools for avoiding thermoacoustic instabilities. Let's learn a little bit more about what all that jargon means. Thermoacoustic instabilities occur in high energy density combustors, such as the ones you might find in aircraft engines, gas turbines, or rocket engines. A flame burning in an enclosed space naturally has fluctuations in the rate of heat release, which produce acoustic waves. These waves can bounce around within the combustor, causing more heat release rate fluctuations. Under the right conditions, or well, the wrong conditions, the heat release rate fluctuations and the sound waves can feed more and more and more energy into each other, and the amplitude of the oscillations can grow devastatingly large and can cause structural damage to the engines. As you might imagine, we as engineers are not too fond of these instabilities. So, what tools do we have at our disposal to fix these if they crop up? The first wall of defense is a good model. If we have an accurate model of the system, we can use it to tweak the design and stabilize the combustor perfectly. However, despite our best efforts, this may not always be possible because the models may be inaccurate or the required tweaks can come into conflict with other design objectives that we might have. We then have to retreat to our second wall, avoiding noise islands, which means that we operate the engine such that we avoid conditions under which thermoacoustic instabilities may be excited. If even this proves impossible, we have to retreat back to the final wall, active high-frequency control. This involves adding just the right kind of pressure oscillations from the outside to exactly counteract any budding thermoacoustic instabilities. However, this is still a mature technology, and engineers typically focus on the first two walls. Let's now have a look at what Bayesian machine learning is and how it might help us strengthen these defenses. Machine learning involves learning some kind of a functional relationship between input variables and output variables. So given values for the inputs, we make predictions about what the outputs should be. Bayesian machine learning does that and more. Together with the prediction, we also get an estimate of how uncertain we are about that prediction, which is crucial when one is trying to deploy these tools in high-stakes environments like an aircraft engine. In this slides, you see a Bayesian algorithm trying to learn the relationship between some variable x and some variable y. The top left image shows the algorithm's predictions when it hasn't observed any data points. It just has a vague prior notion that the variable y should be somewhere around 0. After observing the 6 red data points, so this is the picture on the right, you can see that it has refined its predictions. It now makes predictions with high confidence near the observed data points, but far away from them, it is still unsure. Great. Can these tools help us build better models of our system or optimize them more efficiently? Yes. When modeling the thermoacoustic stability of a combustor, we often rely on reduced order models. But these often have parameters that we do not exactly know. So how do we make these models more accurate? Well, we can use experimental data to find out what the parameters are. In the slides, you see on the left, in red and blue, a simulation generated by a model known as the G-equation model, which models the interaction between a flame and acoustic waves. On the right, in black and white, you see frames from a video of a Bunsen flame in our lab that I took. How do I make sure that the simulations on the left will exactly match what we observe in the real world on the right? We are using a Bayesian neural network trained on many thousands of simulations, which can take in an experimental flame video as its input and spit out the G-equation parameters that would produce exactly that kind of flame, along with the uncertainties in those parameters. Our technique is orders of magnitude faster than the methods that have previously been suggested in the literature. Okay, let's say we have an accurate model of what's going on inside a combustor. Now we need to use it to make design changes that make the combustor more stable. But this model can be expensive, and we can evaluate the stability of only so many designs within our fixed computational budget. This is why we're using Bayesian optimization with derivative information, which helps us find optimal designs more efficiently by using fewer evaluations of the expensive model. We are also investigating how Bayesian machine learning tools might help us dodge those regions of instability more reliably when we're operating the engine. So it has been suggested that the noise produced by a combustor contains clues as to how close it is to becoming thermoacoustically unstable. Let me play a little sound clip for you. Did you catch that little snippet of noise? We have found that in the lab, if you can even feed this tiny bit of noise to a Bayesian neural network, it can then predict how close to an instability our combustor is. We are testing the algorithms that we have developed in the lab out in the real world as well. For example, our collaborators in the German Aerospace Center operate this powerful rocket engine combustor they call BKD, which also exhibits thermoacoustic instabilities. We find that when our tools are applied to data from this combustor, we are able to forecast thermoacoustic instabilities much better using the noise recorded within the combustor. We are also collaborating with gas turbine manufacturers GE and aircraft engine makers Rolls-Royce and exploring how useful our tools can be to them. So that was a very brief overview of my research activities as part of Magister. I hope you enjoyed that, and thanks for watching.